We can start with the introduction. All right, yeah, welcome everyone. It's really a great pleasure to have Monika Schleier-Smith here today as our MCQST Colloquium speaker. So Monika has conducted her undergraduate studies at Harvard. After that, she moved on to MIT to do her PhD under the supervision of Vladan Vuletic. After that, she moved to Munich as a postdoctoral fellow. So you know the community here very well, I suppose, working with Immanuel's group there and also with Uli Schneider. After that, Monika was directly appointed at Stanford, where she is now holding an associate professorship. So Monika has made some groundbreaking contributions to the field of AMO, atomic, molecular, and optical physics, in all of her stages of her career, essentially. At MIT, she was developing essentially squeezing techniques to improve optical clocks beyond the standard quantum limit. After that, in Immanuel's group, she was developing techniques to characterize topological properties of band structures. And now at MIT, Monika is focusing on understanding light-matter interactions in cavities, how to tailor these interactions by strong optical and magnetic pulses, and also she's diving into the field of Rydberg atoms to engineer long-range interactions. And most recently, Monika is interested in understanding how concepts from high-energy physics can be used actually to understand properties of correlated many-body physics pattern. Her career has been awarded with a series of prizes, ranging from an NSF Early Career Award to a MacArthur Fellowship, and now the most recent addition to the collection is the Isaac Rabi Prize from the AMO community of the American Physical Society. So Monika, we are really happy that you're here today and that you are holding this MCQST Colloquium, and we are looking very much forward to your talk on atoms interlinked by light. So the stage is yours, please.
Well, thank you so much for the invitation. It's a pleasure to be back in Munich, even if only virtually. The title of my talk today is Atoms Interlinked by Light, Programmable Interactions and Emergent Geometry. So it's a talk about some work in my group at Stanford on using light to control interactions between laser-cooled atoms. And I should start by just emphasizing that these laser-cooled atoms we really love as just model systems for studying quantum mechanics. And the state of the art, particularly over the past few years, has progressed to the point where these are systems that on the one hand enable single particle control and detection, but also a high degree of scalability, as illustrated by some of these beautiful pictures showing many atoms controlled at the single particle level. And this is kind of this ability of this high level of control is a wonderful starting point for a number of different directions of research, ranging from harnessing the atomic properties to build ultra-stable clocks, aiming to engineer quantum computers, and perhaps somewhat nearer term than kind of building a universal quantum computer out of these building blocks. There's already been rapid progress in the area of simulating certain problems, for example, problems about electrons and materials that naturally map onto systems that one can build out of arrays of these cold atoms. So problems where one cannot calculate the physics classically, but perhaps can learn something by building a model system in the lab. So these are all kind of directions that are explored with cold atoms, and crucial particularly for these efforts in computation and simulation is the fact that one has not only a high degree of control of individual atoms, but also the ability to engineer interactions and entanglement in these systems. And so I've shown here a few different pictures kind of illustrating some of the physics that one sees if one has, for example, atoms that are optically trapped in a lattice of light and can hop between neighboring sites and interact if they're on the same site, right? So this is one standard form of interaction one can have is a direct contact interaction. Here are some pictures, including some from Munich, where that type of interaction gives rise to anti-ferromagnetic ordering of spins encoded in these atoms: spin up, spin down, spin up, spin down. Or similar types of pictures actually can emerge when one has, for example, atoms excited to Rydberg states, which have some longer range interaction on the few micron scale. But nevertheless, kind of one limitation of despite the fact that these interactions already give rise to sort of rich many-body physics and highly entangled states, one limitation is kind of the connectivity of the interactions in these systems. And in particular, the sort of in sort of standard cold atom approaches, atoms only interact with their neighbors. Interactions tend to decay as a function of distance. So why does connectivity matter? I like to sort of start with a classical example. The internet clearly dramatically changes the way that, let's say, we as scientists interact. The fact that we can talk to each other across the globe really has an impact on the way that information flows. So you can imagine in some time before any of us can recall, all that mattered was sort of physical distance, and the people you talked to were sort of your neighbors. But now, these days, I sort of am interacting quite strongly with some network of physicists across the globe, irrespective of how far away they are. What matters is somehow the fact that we're connected by the internet. So connectivity governs the flow of information, and in quantum systems, connectivity also governs, well, for example, the types of entangled resource states that one can prepare. So here are just a couple of examples. If I have a collection of qubits situated on a lattice and nearest neighbors interact, that is a natural way of making something known as a cluster state, that is a resource for computation. But if instead I have a similar form of interaction, but every atom interacts with every other, then that is a natural way of making something known as a squeeze state, which is a resource for enhanced precision measurements. If the interactions are not uniform, but I have some randomness in the graph of interactions, that might actually be a good way of having a system that is highly chaotic, and where information that is initially localized rapidly becomes scrambled. And these types of interactions have been thought of as model systems for studying what happens to information that falls into a black hole. Or if I have sufficiently programmable interactions, then I might be able to take some particular real-world computational problem and map it in some way onto the structure of interactions in the quantum system. And if the problem is, for example, some optimization problem, maybe I can map that to a problem of energy minimization in a physical system and ask, can quantum mechanics help me to solve that problem? So these are a few examples of why you might want control of the connectivity of interactions in your quantum system. And that's sort of by the end of my talk, what we'll be getting to is how can we have kind of versatile control over the graph of interactions in a quantum system. So just to give one more sort of concrete example of what sort of control might you like, I'll take an example from this area of optimization. I like this one because it's the one that perhaps most commonly comes up if you sort of Google quantum and find out what various companies are trying to do in their efforts at quantum information processing. So on the internet, you can find a number of web pages where quantum computing companies will tell you that they are going to solve your scheduling and logistics problems, optimize returns on your financial portfolio, or even optimize fleet operations for deliveries during the holiday season. So what are they doing? How are they going to solve all these optimization problems? There are lots of questions here, by the way, about whether quantum systems can help with these types of problems. If so, what role entanglement plays. One question I always kind of had in my mind is, how do you take some like real world problem and actually map it onto a physical system? So I was really happy when I learned of some examples that I encounter in my real world. So here's one. Let's say you're going grocery shopping. The standard problem you might have is that you have n objects with some particular weights, and you would like to partition them into two bags that you can carry in a balanced way. So you'd like to ask, is there a balanced partition of these weighted objects? And so for certain sets of weights, this is actually a problem with no efficient classical solution. It would take exponential time. If you're a physicist, the way you, of course, would like to solve this problem is you would love to map it onto some spin system. So the basic idea is I could define some quantity that's the imbalance between these two grocery bags. So that's some weighted sum of, well, I'll have a spin that points along plus z, if the object is in the white bag, or along minus z if it's in the green bag. And there's some weight attached to that spin. And the goal is to sort of minimize this imbalance. That's the weighted sum of the spins, right? So if you could minimize this quantity, or you could minimize equivalently the square of the quantity. And if I write that down, that actually looks like some sum of terms that will be positive if the spins are aligned, positive or negative depending whether the spins are aligned or anti-aligned, with some weighted couplings that in this case have some form. In this particular case, the interaction between a given pair of spins would be the product of the weights. But quite generally, this looks like some sort of a system of interacting spins. The interactions are non-local, right? Every spin needs to be able to talk to every other. And there needs to be some programmability of the interactions if you want to encode a specific problem into the system. Okay. So that gives a flavor of some tools that one would love to be able to have in the lab: non-local interactions, programmability of the interactions. And the general approach that we take in our lab to get those ingredients is to let atoms talk to each other with the aid of photons. So the basic idea is that if I have atoms that are coupled to a single mode of light, by exchanging photons amongst each other, every atom can talk to any other. So that gives a non-local character of the interactions. And our objective is going to also be to have not only these non-local interactions, but some programmability by taking advantage of the ability to control the system with light. So before we get to programmability, let's just let me give you a flavor of just how these non-local interactions can work. So the basic concept is that I'll think of an atom with, let's say, two internal states as a spin. So I have these two states, spin up and spin down, which I can think of as kind of an excitation being present or absent in this atom. And if I'd like to make two atoms interact, what I can do is convert a spin excitation into a photon, which gets converted into an excitation in the other atom. And so that is a nice idea, right? That would generate sort of a flip-flop where I went from this spin to that spin being up. Now, one challenge, of course, is that I don't want the photon to just fly off in some random direction. I really want it to be absorbed by the other atom. And so for that reason, we put mirrors around the system, forming an optical resonator that's sort of a box for photons. And within this optical resonator, constructive interference serves to kind of enhance the probability that a photon emitted by one atom interacts again with another atom as opposed to leaving the system. Okay. So that's kind of the general concept, and it's worth pointing out that this general approach of some photon-mediated interactions actually appears in a wide variety of quantum systems that people are building in the lab, ranging from systems of superconducting qubits or quantum dots that talk to each other with the aid of microwave photons, to color centers in solid-state systems that are coupled to nanophotonic devices and talk via optical photons, or the type of system I will talk about where cold atoms interact with the aid of photons. And depending on your application, you might choose one or the other of these platforms. The microwave photon technologies are well established in sort of the quantum circuit applications. One area where the atoms are sort of most well established are in areas of quantum sensing and quantum simulation. And one of the kind of features that's worth pointing out actually in these systems of cold atoms is the scalability. So there are actually experiments at MPQ that have been done generating entanglement between two atoms individually detected here in an optical cavity. And there are also a range of experiments working with systems of order sort of 100,000 atoms. And so that's really, but using the same essential principle of the atoms talking to each other with the aid of the light. I'll be talking today more about this regime of many atoms. And this is one that has already a strong track record in the area of harnessing atom-light interactions to generate entanglement. The general concept is that by having many atoms talking to each other via a single mode of light, that can be an efficient way of building up quantum correlations. And in particular, that's been used by now in a number of groups around the world for manipulating quantum fluctuations and generating quantum states that are squeezed, which is to say, if one looks at sort of the collective magnetization of the system, the quantum fluctuations that in the absence of entanglement would sort of be some Gaussian blob that's isotropic, can be reduced in a particular direction that enhances one's precision measurement. So that's one direction where these atom-light interactions have a strong track record, with applications, for example, to enhancing atomic clocks. A sort of complementary direction that's been explored is harnessing these kind of unusual non-local interactions to explore new directions in simulations of many-body physics. And so that has ranged from realizing super-solid phases to studying systems where one can simulate the sort of solid-state physics of photons using atoms in an intracavity lattice that responds to the atomic motion. To harnessing atoms to manipulate interactions or generate interactions between photons and realize strongly correlated topological states. So these are some of the directions that have been explored. We would like to kind of expand the toolbox and expand what we can do with it. And some of the proposed directions range from broader directions in sort of simulations inspired by condensed matter, such as realizing spin glass phases, all the way to kind of building toy models of quantum gravity, and that's something I'll get to later in my talk. One of the things that I think is worth sort of pointing out as we sort of look at this space of kind of two directions one can explore, the sort of controllable generation of entanglement and the direction of simulation. For me, in some sense, these are kind of two sides of the same coin. In some sense, on the one hand, there have been experiments that generate sort of very specific target states, like these squeeze states, where, again, the ability to have many atoms talk to each other collectively is a resource for generating entanglement, but it's a very simple form of entanglement. And if I can sort of draw these pictures that illustrate some state that has thousands of atoms entangled, and you might say, why am I able to just draw a simple picture? Because in general, the full description of an entangled many-body state shouldn't fit on any classical computer, let alone a picture I can draw. So sort of the point is that these are somehow states that are relatively simple. There are states that have some symmetry that allows us to draw a simple picture of the quantum state. But more generally, we would love to be able to kind of expand what we can do in terms of studying more generic interacting many-body systems in regimes where it is not easy to calculate, and we can apply these systems towards simulating phenomena that aren't classically computable. And in that direction, sort of one of the questions that kind of I always found myself asking is it hopeless to try to visualize these sorts of more complex quantum states that are the target of quantum simulations? And so I was sort of excited when I learned about work going on by people who are thinking about reconciling quantum mechanics and gravity. Because this is something where actually in certain cases, it is conjectured that one can have a strongly interacting quantum system, like some, let's say, one-dimensional chain here, that has some simpler geometrical picture in terms of curved space and gravity in one additional spatial dimension. So the general concept here is that in certain cases, one can have a quantum system with entanglement where something about the structure of entanglement can be captured by a geometrical representation where entanglement is sort of encoded in some notion of distance, if one allows for kind of one extra dimension to encode that notion of distance that says something about the strength of correlations in the quantum system. So this concept is known as holographic duality, holographic because it requires one additional dimension for the gravitational description of the system. And this is something where, when I kind of heard about this, I found myself wondering, well, are there systems where this is something that can be probed experimentally, either in simple model systems or in cases where one doesn't know a priori that such a duality exists, that there's such a picture in terms of geometry and space-time curvature, but where by probing the system, maybe one could find it. So if you'd like to be able to explore that, you would like some kind of predictions coming from the gravity side about the quantum mechanical system. And so from the sort of perspective of people who think about gravity, the simplest system that you could think about and perhaps hope to realize would be something that behaves like a black hole. And essentially what that means is that any information in the system that's initially locally encoded very quickly spreads over all degrees of freedom, becomes, so to say, scrambled and lost to any sort of local measurement. So can you realize systems that do that in the lab? The key ingredient, the key requirement is that one needs to have a scenario where information can spread exponentially quickly from kind of one to many. And this is something that doesn't naturally happen under the influence of kind of local interactions, but there are models that one can write down, at least on paper, that do behave in this way, which have this weird kind of feature of highly non-local interactions. One example is known as the Sachdev-Kitaev model. This is something that involves fermions that can hop in an entirely non-local and correlated fashion. Some of the early actually ideas for how one could realize this sort of fast scrambling behavior also involved not non-local interactions, but behavior that is local in a very exotic geometry. For example, if you have a game of billiards on a tree graph, that can exhibit this kind of exponentially fast spreading of information. So either we need weird non-local interactions, or we need to be able to realize some geometries that don't seem like sort of the geometry of our world, but can we somehow build these in the lab? Okay, well, I already gave you a flavor of how one can realize a situation where particles hop non-locally. In our case, not massive particles, but spin excitations, right? So I said we can convert a spin excitation into a photon into a spin excitation in another atom. And so that will be kind of the first thing that we can do in the flavor of starting to study some of these more exotic models, perhaps inspired by quantum gravity. So let's just say a little bit more concretely how that works. I gave you a cartoon picture earlier, but I want to emphasize what we would like is to have a system where we can actually optically control these interactions. So concretely, we have our atoms trapped in this optical resonator, and we arrange a situation where we drive it with light in order to generate a spin exchange interaction mediated by light. So we'll have a situation where an atom can absorb a photon from a control field that I've shown here in purple, emit it into the resonator, and another atom can absorb a photon from the resonator and re-emit into the control field, each of these atoms flipping its spin in the process. So that will give us an optically controlled spin exchange interaction. The setting where we do this is this resonator literally consists of just two mirrors, about 5 centimeters apart. We have atoms that are trapped in a standing wave of light between those two mirrors. And I'll emphasize that sort of the motion of the atoms, the motional degree of freedom is frozen out by a lattice in which they are trapped. And so the dynamics we'll be looking at is just in the internal states, in the spin degree of freedom. So just as an example, here's an experiment where at time t equals 0, we had essentially a cloud of atoms along this cavity axis, where we created some spin excitations locally in this region that I call A. At t equals 0, we turned on the light that turns on the interactions and kind of watched where the spin excitations go, and you can see them hop over to this region B and hop back. And this kind of nicely illustrates the non-local character of the interactions. The spin excitations don't just kind of propagate outward, they suddenly show out over here. Why do they show up there? That's actually something that one can model and understand very well if we just know the local density of atoms and the local intensity of the light field. In this particular case, the intensity of the light field of the cavity mode is strongest towards the left side. This is actually the center of the cavity, and that's why the spin excitations kind of hop over here first. Okay, and one can see at any given position some oscillations in the magnetization that are a signature of coherence in the system. Okay, so this is starting to see non-local interactions. It's not yet programmable interactions, which I said was our goal. And so, we would love for this to be kind of, a function generator for engineering the interactions that we can realize. And I mentioned one knob that we would like is to control the graph of the interaction. Other things you might like is to control the type of the interaction. So do we have this sort of Ising type interaction where the spins want to align or anti-align along Z? That was something I brought up in the context of optimization problems earlier. Or do I want this sort of flip-flop or spin exchange type interaction where excitations can hop between different atoms? I'll also call that an XY interaction, because I could rewrite that as saying that the X and Y components of the spins want to either align or anti-align. So that's a knob we might want on our function generator. Or maybe the sign of the interaction. Are the interactions ferromagnetic or anti-ferromagnetic? Do the spins want to align or anti-align? Okay, so just as kind of a warm-up before we get to the spatial structure, I'll say a little bit about what we can do in terms of controlling the form and the sign of the interaction in the case where every atom talks to every other. And so actually in the case where every atom talks to every other, I can think of the cavity as essentially talking to some collective spin that's a sum of the spins of the individual atoms, perhaps with some weights. And in terms of that, one of the neat things that we can already start to do is actually control what is the form of the interaction. Do the spins want to align or anti-align, and do they want to do so along Z or in the XY plane? So it turns out actually in this system, simply by changing the orientation of a magnetic field relative to the axis of the resonator, we can dictate whether the interaction is an Ising type interaction where the Z components interact or an XY type interaction. One way you can think about this is that when I sort of write down my Hamiltonian, I am working with a quantization axis that is set by my magnetic field. And depending on the tilt of the magnetic field, so the Z component is along the field. If the field is along the cavity, the Z component of the spins is along the cavity and actually couples to the polarization of the light. If the field is perpendicular, the X and Y components will alternatingly couple to the cavity and couple to the polarization of the light, and that is the mechanism for generating an interaction. Okay, and so we can control the form of the couplings with a magnetic field. We can control actually the sign of the interaction just by a laser frequency. So this is just kind of illustrating that we can have arbitrary control here of those sort of two ingredients of the structure of the interactions. To give kind of a flavor of one thing you can do with this, here's an example of an experiment where we measured the magnetic susceptibility of a system with either Ising or XY interactions in an applied field. And one of the kind of neat things that one can see in this situation is that there's actually a mirror symmetry where the system with ferromagnetic Ising interactions, the spins want to align along Z, looks identical to the system with anti-ferromagnetic interactions in the XY plane. So in each case, there's some point where the magnetic susceptibility diverges. This has to do with a phase transition where the spins want to align with each other along Z, transition to a ferromagnetic state. But interestingly, the same thing happens with anti-ferromagnetic interactions in the XY directions. So why is this the case? It turns out that one can actually understand this from some symmetry. If I think of the system as acting as a single large spin, because it's coupling to this single mode of light, then I can use this relation that the square of the Z component of that big spin is the same as minus the squares of the X and Y components up to some added term that depends on the total length of the spin. Okay, so these aren't exactly the same. But at any sort of fixed total length of the spin, actually, if I plot sort of the energy versus Fz and Fx, it looks the same. In other words, these two forms of interaction are actually equivalent if I constrain myself, if I initiate the system, let's say, in a spin polarized state, and I don't do anything that breaks the symmetry between the individual spins. Now, there is a key difference, though, between these two scenarios, which is that if I am allowed to change the length of the spin, there's actually an energy penalty for doing that in the case where the interactions are in the X and Y components, which isn't there if I have purely Ising interactions. And so it has been pointed out that this ought to allow you to use interactions to actually prevent the individual spins from dephasing. And this is actually something we can directly study in our system. So here's an example where we look at the dynamical response of the spins to an inhomogeneous magnetic field. So there's a magnetic field gradient in the system. Actually, even without trying, sometimes there's a small magnetic field gradient in our system. And if you have no interactions, you'll see some spiral texture appearing that shows kind of the spins winding in that magnetic field gradient. But if we turn on actually these XY interactions, the spins are locked to each other. This picture of the phase versus position and time looks completely boring because the spins are staying aligned. We can summarize that by looking at kind of the phase winding across our cloud as a function of time, either where we have XY interactions or no interactions or Ising interactions. And the phase winds for no interactions, it winds for Ising interactions, but that phase winding is completely suppressed if we have these XY interactions. And so one can see that there's some strength of the XY interactions that ensures that the contrast of the system, so the total magnetization of the system remains high. And this is kind of a neat effect where interactions are really being used to protect the coherence of the quantum system. This is something that, so, you know, where might you use this? Particularly if you're using the light anyway, perhaps to generate some entangled state is something that's done. You might prefer to choose the interactions that will, while you're at it, also give you this added robustness to any effects that would cause the spins to dephase and allow you, particularly, for example, for applications in quantum sensing where one wants a large spin for a large signal to noise, this can be a useful mechanism for preventing dephasing. But also I'll mention the same mechanism has been proposed as something that could be applied in systems where one wants to generate collective entangled states using short-range interactions. And so this could also have applications in other systems, such as systems with Rydberg interactions. Okay, so I've shown you some tunability of the form of interactions. One can just simply by control of a magnetic field, control do we have Ising interactions or these spin exchange interactions that can protect the quantum coherence. Before I go on, I'm actually going to pause. I don't know whether you take questions, but I want to pause and ask whether there are questions, just to break things up.
Yeah, in principle, we could also do the colloquium.
So I'm not talking to an empty screen.
So Monika, the strength, you didn't say anything, or maybe I missed it, on the absolute strength, the scale of the interactions.
Yeah. So the characteristic sort of time scales of these experiments are on the sort of 100 microsecond to few millisecond time scale, and that's kind of set by the mean field interaction typically being a few kilohertz. So if I take one spin and I ask what is the strength of interaction with all the other spins.
Mm-hmm. So kilohertz-ish.
Kilohertz-ish, yeah, again, and this is collectively enhanced.
Okay, good.
Yeah.
I also have a question regarding the realization of SYK type models. So is it actually possible in your system to fully get rid of mean field shifts so that you don't have something like HI-SI so that you really map onto a direct SYK type model? Or do you always get these slight shifts SIC also in addition?
So that's an interesting question. So do we always get, okay, so normally a local field, you're asking whether we can avoid having any local fields.
Yes. So I mean, the question is, because I think, I mean, in some sense, what I'm thinking about from the theory perspective, we have this, when we map the spin before Stern-Primakov onto particles like bosons or fermions, then the two spin operations will give you the quartic terms, which are then characteristic for this growth, right? But as soon as you have a quadratic contribution, then your system flows into a Fermi-liquid type phase. So this means whenever you have some random light shifts coupling to SC, that you would see asymptotically this Fermi-liquid type.
So in general, to the extent that there are light shifts, these are things that we can compensate, and then there's maybe a question of how well one has to do that. Overall, there's not, I mean, there are always perhaps some imperfections, but overall we can be operating in a uniform field. I think the thing that I always thought is the bigger concern, and maybe I'm not sure whether this was a part of your question, is that we naturally get sort of two-body terms. right? The spin excitations hop. It's not quite like an SYK where there are these four-body terms where you have pairwise correlated hopping. And so some people have asked me, isn't that a problem for the low temperature physics? They're also not fermions, right? So it's certainly not exactly SYK. And I sort of think of it as something that is similar in flavor, and from the perspective of sort of at high energy density, the dynamics could have similar behavior if the couplings are random enough, which is not the case in what I've shown you so far, actually.
I think, I mean, the original ideas by Subia, they were a bit in this direction, that you have a random magnet, right? So similar to what you were realizing. So in that sense, I was more wondering really about these HI, as I said, terms or something like this, where you can fully get rid of.
So in general, those terms, there are not, ideally we don't have local fields that are inhomogeneous. To the extent that they're there, we have ways of compensating them.
I see.
So, yeah.
Okay, thank you. Yeah, are there further questions by the audience? A good time to continue discussions.
Okay, so I just wanted to at least briefly pause to break things up a bit. So far, some of what I showed you before, I sort of, you could almost understand in kind of a mean field picture of spins responding to some effective field from the surrounding spins. To give a little bit more of a flavor that there's something quantum going on, I'm going to sort of add one more piece of the story here. So it turns out one way that we actually can probe the system is actually taking advantage of the spin 1 structure of our atoms. I swept that under the rug before, it wasn't important, but we actually work with rubidium atoms that have a spin 1 ground state. And one type of experiment we can do in the system is initiate the system in the situation where all of the atoms are in the m equals 0 state of this spin 1 ground state, so the system has no net magnetization. And so naively, if you take my picture of the magnetization coupling to the polarization of the light, you might think nothing will happen. But actually, if I say that I have, let's say, this spin exchange type of an interaction, an F plus, F minus, I should be able to have 2 zero atoms turn into a +1 -1 pair. And that's indeed something that happens in the system if you start with all atoms in the 0 state and turn on the light that turns on interactions. As a function of time, you'll see, if I do look at a fixed time after I turn on the interactions and repeat that experiment 100 times, what you'll see is that often there's now some population appearing in the -1 state and the +1 state. There's some fluctuations, but they seem to be correlated, right? So when I see population in the -1 state, there's also more population in the +1 state. And this is consistent with this picture of generating actually by these photon-mediated interactions, correlated atom pairs in the -1 and +1 states. This is an analog of a process that is actually well studied by collisional interactions in Bose-Einstein condensates, where two atoms in the 0 state can collide and make a +1 -1 pair. In that context, it's actually been used to make highly entangled so-called twin Fock states, where you have exactly the same number of atoms in the -1 and the +1 state, but no idea which atom is in which state, which are resources actually in quantum sensing. But one of the things that kind of is neat about being able to do this now in a way that is in this spatially extended cloud of atoms where interactions are controlled by light is that perhaps we can start to control also the spatial structure of the correlations in the system by suitable optical control, if we can start to kind of optically control more about the structure of the interactions. And so in order to kind of cleanly start to study that, I'll show you now experiments where we're working in an array of atomic ensembles. In this case, we typically have about, let's say, 18 atomic ensembles. Each one consists of thousands of atoms. This is beneficial because it gives us some collective enhancement in the interaction strength. And we would love to be able to control, basically, arbitrarily the graph of interactions between these ensembles. We'll be a little bit less ambitious and say, let's not aim for complete arbitrary control, but let's ask whether we can make any graph of translation invariant coupling. So how much control can we get of the interactions versus distance in this system? And we're actually inspired here by a clever proposal from Ignacio Sirac and Jeff Kimball and collaborators. So, okay, so what's the idea? How do we start to control the graph of interactions? The first thing that we need to do is actually turn off the kind of all-to-all part of the interaction, where every atom talks to every other, if we'd like to get more control. And the way that we can do that is to apply a magnetic field gradient across our system. So here is actually a plot where I'm showing you basically the spatial structure of correlations. What is the correlation? So we start with all atoms in the 0 state, we initiate this pair creation process, and we ask what is the correlation between the number of +1 atoms on site I and the number of -1 atoms on site J. And in this particular case, what you see when we have just this magnetic field gradient is that the correlations are strong on the diagonal, which is saying that these pairs are only forming locally on individual sites and not at a distance. And that's because there's an energy penalty. The cost of creating a +1 -1 pair at a distance, there's a cost because of this magnetic field gradient. But we can bridge that cost by driving our system with 2 control fields. So the basic idea is if we can have a situation where we absorb a photon from one of these one frequency and emit a photon of another frequency, that frequency difference can bridge the cost of now creating a +1 -1 pair at some distance. And that shows up in this correlation plot as these off-diagonal features, where in this case we have correlations at a distance of 10 sites coming from modulating our drive field at an appropriate frequency. And so more generally, if we ask, if we scan the frequency with which we are modulating our drive laser, so the vertical axis here is the modulation frequency of our drive laser, the horizontal axis is showing correlations as a function of distance, you'll see that the distance where these correlations appear tracks. And so this is showing that we can controllably turn on interactions at a distance specified by the modulation frequency of the drive laser. And you can see there's actually quite a high level of control. So we can control the interactions at a distance of 9 sites or 10 sites or 11 sites just by controlling the frequency.
Monika, there seem to be additional branches there. Also the one with the lower slope, what are they?
That is a great question. So somewhere there's an extra slide. I think I won't jump to it right now, although if you're curious, I can show it at the end. But this is actually, you might wonder, are there like higher harmonics in the drive field that are generating these? And we thought, maybe it's higher harmonics, or is it information actually or correlation spreading, right? Because we had the light on for some particular time. So this is actually correlations that have spread beyond, in this case, there's interactions at a distance of 2 sites, but these correlations can spread to 4 and 6 and 8 sites. And so that's what's going on. If you ask me again at the end, I can show the time evolution. Okay, so good. So, but now we can also generalize this. So if we have multiple frequencies in my drive field, I could imagine having more versatile control over the couplings, right? Okay, so one thing we can do, for example, is to pulse the drive field at a higher frequency. So here's an example where actually, what I showed you before, there's sort of a continuous sinusoidal modulation. The modulation frequency dictates the distance at which interactions are on. But it turns out if, in addition, we pulse this drive waveform at a frequency that would correspond to kind of the length of the chain, this actually allows us to have interactions at not only the sort of distance specified by this modulation, but also at the length of chain minus that distance. And this generates periodic boundary conditions, right? So like if we had interactions here at a distance of 3 sites, but also at a distance of 18 minus 3 sites. So this is actually a very general technique by adding this additional pulsing for converting, let's say, an open chain into a ring. Okay, so we can generate periodic boundary conditions. I told you that based on this correlation plot, and this starts to kind of show that the geometry of the graph of interactions doesn't have to be the same as the physical geometry in the lab. We can actually kind of verify that a bit more directly. My student said, well, let's see, can we just directly from the measured data infer what is effectively the geometry of this system? So here's an example where, again, we have sort of nearest neighbor interactions, but also periodic boundary conditions, and the sort of waveform we apply is designed to do that. You can say, let's adopt some ansatz of these sites having some effective geometry, and correlations should decay as a function of distance in that effective geometry. And now we can ask kind of what is the best fit embedding of the sites into, let's say, 3 dimensions to explain the correlations that we measure. And indeed, if you, you can kind of, essentially it's a least squares fit to find that best fit geometry, and it looks a lot like a ring. So that looks good. And I'll emphasize that actually what's drawn here, every possible bond between pairs of sites is drawn here. So there are order n squared possible bonds, but the opacity is indicative of the strength of correlation, and the color is indicative of the sign of correlation. And what you see is that the ring is kind of what pops out here. Okay, so this is a nice kind of black box technique for checking what is the interaction graph that we've created, and we can apply that to a couple of other scenarios. So for example, if we have just interactions at a distance of 3 sites, let's say, and open boundary conditions, if you apply this same technique, you can think about what you expect to pop out in the reconstructed geometry. This gives you a set of 3D coupled chains, and that makes sense because I could have actually drawn this graph in a different way. Site 0 is connected to 3, 6, 9, and so forth, but not to site 1. Okay, we can, so this gives us sort of a set of 1D systems, but you could also add additional bonds. So here I have nearest neighbor interactions, periodic boundary conditions, and while we're at it, we said let's add some interactions kind of across the ring here. We can actually control the sign of the interaction by the phase of the modulation at the corresponding frequency. So in this case, we said let's have them ferromagnetic between neighbors and anti-ferromagnetic across the ring. You measure some correlations, and now, again, you can stop and think what is the kind of effective geometry that's going to pop out when we reconstruct. And what you find here, in this case, is a Möbius strip. And so this makes sense, right? So we have kind of this ring here is the single edge of the strip, and these bonds across are kind of these legs here of this sort of ladder. And so this kind of illustrates, I think, starts to illustrate the power of this method for generating some unusual geometries that aren't so natural to realize by other methods. One can also look at kind of the sign of the correlations and infer something about the sort of actually the spin texture in the XY plane that's generated by these dynamics. So in this particular case, these ferromagnetic bonds result in the spins being almost aligned between neighbors, but actually they're anti-aligned across the ring. So we can interpret this as a spin texture that's kind of winding about the single edge of the Möbius strip. Okay, and now you can play games and sort of program different waveforms and see what geometry pops out. Right, so we can make a cylinder without a twist. We can control whether the interactions in the Möbius strip are, sign changing as they were here, or all anti-ferromagnetic. We can make a ladder type geometry. And again, this is all just changing the modulation waveform of the drive field. One quick point I want to emphasize here, it's sort of not obvious that just by controlling the sign of the interactions, in this sort of we suddenly quench on the interactions. It's not immediately obvious why the sign of the correlations should sort of match the sign of the interactions. I didn't tell you we adiabatically prepared a ground state. But one of the kind of neat features of these dynamics is that this pair creation process actually kind of lowers the interaction energy at the expense of an increase in quadratic Zeeman energy. So for a single atom, actually the +1 and -1 pair has a higher energy than the 2, 0, 0 state. So that allows the system to lower its interaction energy by creating these pairs. And so, for example, if you have now some system where the interactions are frustrated, maybe it's not obvious how the spins should align or anti-align to minimize their energy, maybe this can be a system, these dynamics can be used to actually find low energy states. So in this example where we engineered, let's say, an XY interaction with fully anti-ferromagnetic interactions on this ladder, the spin correlations are consistent with the spins kind of doing the best to minimize their energy by some roughly 120-degree ordering, where the nearest neighbors are mostly anti-aligned, but third neighbors are kind of aligned again. So from these spin correlations, we see evidence that actually the system is finding kind of low energy states of these interaction Hamiltonians. Okay, so we can realize some rather exotic geometries, non-trivial topologies like this twist of the Möbius strip, frustration, these interactions that have different signs at different distances can also give rise to frustration and are of interest for actually simulating spin glasses and condensed matter physics. One could imagine going further and then controlling the sign and even controlling the phases of the couplings. This is something that I learned a lot about in Munich from the beautiful work in Emmanuel's group on generating synthetic gauge fields. These are ingredients that one could also now explore perhaps in some more exotic geometries. Some of the things, again, that I've shown here are kind of inspired by things you can do in other platforms, so that you could also use local interactions to realize something like this antiferromagnetic ladder. So in the last few minutes, I want to say a little bit about sort of exotic things that are hard to do by any other method. And so we'll, again, sort of ask this question of, can we build some toy models for studying this idea of holographic duality and quantum gravity? And so I have to now admit that I actually know very little about, I'm pretty comfortable with quantum mechanics. I don't know so much about gravity, so I was very fortunate actually to get to collaborate with a true expert, Steve Gubser, who was really interested in understanding the question, kind of what is the mathematics underlying the reality that we experience as kind of smooth space-time, but which we have reason to believe is discrete fundamentally because of quantum mechanics and the existence of a Planck length. And Steve had formulated kind of a version of this holographic duality where the quantum system lives on the boundary of some higher dimensional space that has curvature and gravity, where that higher dimensional space, the so-called bulk, actually takes the form of a tree graph. So the idea is you have some system that lives on the leaves of the tree, but the structure of quantum correlations is somehow encoded by this tree graph. And the tree graph, you can think of, why is this like a curved space? Well, the sort of base of the tree has n sites, the depth of the tree is log n, and so here I've shown it kind of wrapped around with periodic boundary conditions. If my circumference is n, but the radius is log n, this must actually be a negatively curved space. So this is kind of a discretized version of anti-de Sitter space. And so the question is, could you realize kind of a physical system where this tree graph emerges as kind of the natural description of the structure of quantum correlations? So there are actually systems of superconducting qubits where people directly engineer some of these kind of hyperbolic geometries. But we're again kind of interested in the question of can this tree graph emerge not as something that we program in, but something that describes the structure of the quantum correlations in our physical system. So there's a toy model that we realized might do this. And the basic idea is one has a chain of an array of sites where the interactions are between sites separated by a distance that is a power of 2. So 1, 2, 4, 8, and so forth. At all of those distances, we want interactions. And you can now imagine a couple different scenarios. You could have the interactions, you could add some power law exponent where the interactions either decay with distance or grow with distance. If they decay with distance, it's not so different from having like a linear spin chain. The strongest interactions are between nearest neighbors. So that's one limit. This exponent is less than 0. If the exponent is greater than 0, it's kind of a weird looking graph. The strongest interactions are between furthest neighbors. I could actually rearrange the sites in a way that I can sort of, some of the most strongly interacting ones are closest together. And if you do this, you might start to see, or maybe you don't quite see it yet, that this has a little bit of a flavor of a tree-like structure. Okay, so I'll try to convince you a bit more that this is the right way to think about this system. So the first thing we did now in the experiment is program in the structure of interactions that are at distances that are powers of 2 and that grow with distance. And what you'll see is that basically when we measure the correlations arising from that structure of interactions, there's some non-monotonic structure where the correlations are also strong at distances that are powers of 2. And if we want to see whether this really is behaving like this tree graph, what we can do is actually kind of rearrange the sites according to their position on this supposed tree graph that might describe the structure of the quantum correlation. So how should I rearrange the sites? The tree graph is basically, what it's saying is basically the way I've, due to the structure of interactions, the odd sites and the even sites have the weakest connections between them. And so those are sort of the two halves of the tree. And more generally, I should basically define the position on the tree. I should look at whether the least significant bit is a 0 or 1, go left or right, and repeat that process for increasingly significant bits. So to find the position on the tree, you reverse the order of bits in the site index. And if you organize the sites in that way, then this correlation plot starts to have kind of a block structure that is certainly kind of more sensible looking than what we saw for the physical ordering. These blocks are some indication of kind of the hierarchical structure of the tree. And if you plot the correlations versus the correct measure of distance on the tree, they smoothly decay. Okay, so that's starting to indicate that maybe we really have this tree-like geometry. We can take this one step further and ask, can we reconstruct this in a black box way just from the experimental data? And so we'll take the same approach we did before to ask sort of what is the best fit embedding of the sites, in this case in 2 dimensions, to explain the quantum correlations, to explain the correlations that we measure. And now, though, what we'll do is actually adopt kind of a coarse graining procedure and ask which of these sites, which pairs of sites, or at what distance are the sites most strongly correlated. And we'll draw bonds between the most strongly correlated sites, treat those as a larger site, repeat that process until everything is connected. And what happens when we do that is actually we can precisely arrive at this tree. That's true in the case where interactions are growing with distance in the physical system. If they're shrinking with distance, so it's more like a spin chain, then this gives sort of a trivial circle here. But the tree emerges when we actually do this sort of coarse graining procedure for this more exotic structure of interactions. And just sort of as a final note, kind of one thing that this coarse graining procedure is also showing us is sort of where would you cut the system if you wanted to divide it into 2 halves that are kind of weakly correlated with each other, sort of where, sort of what is, it gives some measure of the sense of locality, what's close together, what's far apart. And you can ask the same question as a function of that exponent that tunes you between the linear and the tree-like geometry. So, you know, if we have this kind of thing that's roughly just a spin chain with periodic boundary conditions, then, and if you cut according to that physical geometry, then that's sort of showing the blue points here, the correlation between the 2 halves of the system is low. But if you had the tree-like graph and you cut it in the same way, the correlation would be strong because you haven't correctly cut it according to the geometry of the system. Similarly, to make the correlations weak between the 2 halves for the sort of tree-like structure of the interactions, you need to cut according to the tree. That's the green is showing what happens if you cut according to the tree. But actually, if you sit at the place where this exponent is 0 that dictates whether interactions shrink or grow with distance, then there's actually no way of cutting the system so that the correlations between the 2 halves are weak. And so this peak is kind of saying there's actually a regime in between the linear geometry and the tree-like geometry where everything is strongly connected to everything. There's really no sense of locality. And our conjecture is that this could be actually an ideal condition for realizing fast scrambling. And so you can read more about, to the extent that we were able to calculate things, that was something we looked at in this theory paper, but eventually one should actually simulate this in the lab. So with that, I will just kind of conclude and say I've shown you a range of sort of ways in which we can program the interactions in our quantum system. We have control over the graph of interactions, the geometry and topology, the sign of interactions, the form of the couplings, and I'll briefly mention if all of these exotic non-local interactions are too much for you, we do also work in our group with local Rydberg interactions and optical control of those interactions, and that's a story for another day. But for now, I'll just mention that we are really kind of excited about the prospect of, first of all, having kind of this tool for reconstructing the geometry directly from the spin correlations. That could be a starting point for some broader explorations of this concept of what are the cases where there's some emergent geometry that is a natural description of the quantum system, and exploring deeper this idea of holographic duality in the lab. We're also interested in taking advantage of the fact that this pair creation physics naturally kind of amplifies low energy configurations of this XY interaction, as potentially a tool for exploring some quantum approaches to solving optimization problems that can be encoded in interacting spin models. It's an open question, sort of whether that will give a quantum advantage. So I'll just briefly mention that sort of while shut out of the lab, we also thought a little bit about ways of solving that number partitioning problem I mentioned at the outset in a way that would in fact demonstrably give a quantum advantage, and that's applying Grover's algorithm to solve this particular class of optimization problems. That's something you can read about here. And lastly, I think we're interested in taking these programmable interactions also as a tool for generating a range of different entangled states that might have applications ranging from sensing to computation. And with that, I will just thank the team, particularly Eric Cooper, Avakar Parawal, Philip Kunkel are the ones who have done these latest experiments on the programmable interactions, and all of these folks in red contributed to things I talked about today.
Yeah, thank you very much, Monika, for this very nice and inspiring talk. Now it's time for questions. We have to clap virtually, unfortunately, right? So we don't.
Yeah.
Maybe we should play a sound of clapping audience at some point. This would
Can I start? Just, Michael, I have a few fundamental, Monika, yeah, thanks for the exciting talk. I have just a few basic questions to start with. So to get the feeling, so the drive you apply, that's done along the cavity, just some Raman transitions along the cavity, I guess, axis, correct?
Yeah, so we drive along the cavity, and the light is, it's detuned from resonance, right? But nevertheless, it's close enough that if you send in enough power, some light goes in. Okay, driving so along,
it's off the resonance, off the cavity resonance, but still it's, you see enough light gets in to drive that.
Yeah, it's off of cavity resonance, and it's also somewhat off of the 2-photon resonance that would flip a single spin, so that what's resonant are these kind of pairwise plot processes.
Okay, can you explain again how you do the readout of the spins? I get to what you've shown so far are all measurements in the same basis, where you do SZ correlations, for example, across. Maybe you can first explain.
This is a good question because actually I sort of glossed over this. So we actually aren't doing all the measurements in the same basis.
Okay, so maybe you can first explain how you do the measurement at the single site, how you.
Yeah, so the way that we do the measurements is essentially we do state-sensitive imaging by having a sequence of fluorescence images that measure, we take the 1 - 1 atoms, sweep them into F = 2, do a fluorescence image, and then that also pushes the atoms away, and then we do a second image of the atoms that were in 1, 0, and the third image of the atoms that were in 1, 1. So we do it this sequence of 3 images that shows us basically in a site-resolved way, the population in each internal state.
Okay, so you say you get maps, spatial maps, just by spatial resolution of your optical system. You take a fluorescence image and you just see the spatial maps of those different spins.
Exactly, yeah. So it's basically each individual sorry, can I just want to navigate to where I can.
Right, so you could change the measurement basis by doing some rotation.
But we do change the measurement basis, actually, and I glossed over that. So actually, the very first measurements I showed you were correlations between +1 and -1 atoms. But later, we actually find that we have higher sensitivity if we just create a small number of atoms in +1 and -1. We have higher sensitivity by measuring in the X basis. And so we can essentially so this is actually non-trivial. So you need to do, we end up doing a local rotation on each site with a focused Raman laser. And this is because we have a magnetic field gradient on, and each of those rotations needs to be with a slightly different frequency. So it's actually, I was actually sort of amazed that this worked. Like really there's a sequence of rotations on each site. In principle, you could choose any basis on each site.
But
is that making sense?
Yeah. Singles, I mean, when we talk about single sites, what are we talking about? I mean,
but for us, again, so this is like the spatial resolution required is very low because the interactions are mediated by the cavity. So this whole chain is about 1 millimeter long. So there's about 50 microns between, right? So it's not demanding from the perspective of spatial resolution.
I see.
Because the interactions are so long ranged.
Okay.
Yeah. But it is a sort of non-trivial sequence where I think the good thing to point out is, yes, we actually can choose independently on each site our measurement basis. So far, we've always done either everything in the Z basis or everything in the X basis. And these measurements in the X basis, again, give better signal to noise. And actually, maybe I'll just, because you asked about this earlier, I'm just briefly going to show one more thing. So there should be a better way of, there should be a better way of flipping here. But so actually, if we do, for example, this is a measurement, the first motivation for doing measurements in the X basis was asking, can we get better sort of signal to noise at early times in order to watch kind of how the correlations grow and spread? So this is a question you asked earlier, sort of as a function of time. If you measure these correlations in the X basis, you can see that they appear first between sort of in this case, where interactions are at a distance of 3 sites, first between third neighbors, then between sixth neighbors, and they spread. And the other nice thing is this is something you can Fourier transform to get sort of a structure factor and ask in momentum space about the dynamics. And there one can think of it as kind of a peak that's growing at a particular momentum. So
maybe I would have a bit of a related question. So so you essentially have many atoms trapped in one well, right, of your optical potentials, 1,000 atoms. So you think about a big spin. But when you drive now the transition with your external field, what are you precisely driving? Are these single excitations which you're moving from one, or is it like a big transfer of excitations? You know what I mean, roughly? You have some S plus
I'm
S
not
minus
quite
terms.
sure which.
Can I think of it as moving a big collective spin by a little quantum, or is it really transferring a lot of excitations from one?
Are you asking about the effect of the interactions, or when we do some local rotations?
No, I thought that when you apply additional modulation fields to drive essentially in a particular distance a flip-flop or something like this.
Yeah, so I should emphasize this is all the field that is driving the cavity. So it's just the same light that would normally be used to turn on interactions, but now it's modulated.
Yes.
But I guess what Michael is asking is flip-flop individual spins.
Oh.
Spins
I like to think about the Hamiltonian.
Yeah. Okay. So in some sense, I can write the form of the interaction down either way. I can write it as pairwise interactions, or I can write it in terms of something that is the sum of individual spins on a site, because of the sort of symmetry that all of the atoms on a given site.
Are you transferring a single excitation over to the other side, or is it like?
But what we're measuring are many excitations, right? So typically in the experiments I've shown you, we drive these interactions long enough that maybe 30% of the atoms are in the plus and minus ones.
More like in the Fermi-Scold rule, you have a continuous process of driving excitations or shuffling excitations from one side.
Yeah, but I think one thing to be careful about when we say, should I think of it as a single large spin, is that we are taking advantage of the internal state control, right? It's not starting in really a spin polarized state, at least in the normal sense. It's starting with all atoms in this zero state, right? So,
yes.
Yeah.
Okay, thank you. Yeah, there's another question by Hans, who has raised his hand.
Yeah, thank you for this overview talk. I think already I learned a lot, but I have a kind of maybe extremely naive question because I'm not in the field. So you use this modulation waveform as you describe here, and you have basically two-dimensional control, or I would see this as a two-dimensional control of amplitude and phase of this modulation waveform. So does this limit the geometric constructs that you can fabricate or synthesize in terms of interaction in some way, or is there basically no limitation?
So we can control the spectra. So we don't really have only amplitude and phase, because we have the amplitude and phase at different frequencies. Right, so sorry, we have amplitude and phase, but we also have a number of different frequency components that we can add to this waveform. And so that, by selecting a given modulation frequency, we turn on interactions at a particular distance, and the amplitude and the phase dictate the strength and the phase of the coupling at that distance. And now, basically, one way I almost think of it is kind of for each new distance, in these pictures where we were showing some kind of new effective geometries, it's almost like each new distance kind of adds some effective additional kind of dimension to the graph of interactions, potentially. So it's
okay, but
quite
then
rich.
You are basically in a multi-frequency regime, and then you should be able to do almost anything if you're not running into the problem with modulation bandwidth, so that the frequency starts to overlap. Then you're running into an issue potentially.
Yeah, and I think so far that's not really the limitation. The limitation probably has more to do with just kind of how many individually resolved clouds of atoms can we easily fit into the strongly coupled region of the cavity. And even that, I think, could be pushed probably to sort of order 100.
Okay.
Yeah.
Thank you.
Mm-hmm.
Thank you. Further questions? Monika, maybe I have another one. So when you kind of said that you have on a two-leg ladder, you find triangular orientations of the spins, right? So how can I think about this now? So this would be, how can I think about that you really reach the ground state manifold of the system? I didn't understand, but you already explained it, I think, in the talk, but I didn't quite.
Yeah. Let me give kind of actually a complementary picture that will use the slide that I happen to be showing here right now. So one way that we actually think of this is in the same way that the spectrum of our laser controls the distance at which interactions are on. You can sort of also Fourier transform this picture and say the waveform with which I modulate the laser controls the dispersion relation, so the energy versus momentum. And now one of the kind of neat features of this system is that this pair creation, there's really an instability to forming these ±1 pairs. And so there's, if I had just a single mode, the population in the plus and minus one states would grow exponentially. In this case, where we have this kind of spatial control, actually you can kind of ask about what is the growth rate as a function of momentum. And actually the sort of minimum energy, so the minima of the dispersion relation actually correspond to the maximum growth rate.
That's engineer ordered states, right? So I mean, this is important somehow because the quantum, I'm not allowed to think about quantum correlations per se, right? This would be a next level essentially on top, right? Just to get the fluctuations, right? This is a different story in some sense, right?
Say that again, to get the fluctuations.
I mean, what you are kind of creating by these by these modulation patterns is that you can create essentially, by instability, you drive into certain states, which is essentially long-range order, right? But fluctuations around this long-range order is somehow which is more complicated, presumably, to control, right? So
right.
This is
I'm not exactly. I'm not precisely sure how to think about the influence of fluctuations, but I think this at least gives a picture for why sort of what's amplified are sort of these low energy modes.
Perfect.
Yeah,
thanks a lot.
Yeah.
Good. Further questions? Last chance. Okay, so this doesn't seem to be the case. Then thanks again, Monika, for this very nice talk. It was really great.
Was there one more person who just I just saw somebody unhide their video, so I was wondering if there's one more question. Yeah,
I actually had a short question about the holographic duality that you talked about. So you said that that meant that in certain entanglement states, if you describe them in another geometry, they're entangled in such a way that it seems like they are in another geometry, and then can you actually write them down in this new geometry in a non-entangled way? So if you somehow use the different basis states or something.
So first of all, I should emphasize I didn't actually prove anything about entanglement in these measurements. Just to sort of I don't want to oversell here. Our understanding is that we're creating these correlated pairs, and should be entanglement. And one of the next things we're doing is actually saying, can we measure that and show that? But I would say that there certainly. So again, in the case where one has just a single spatial mode, these dynamics should be giving rise to this form of entanglement where you sort of know that if there are more atoms, you have the same number of atoms in +1 and -1, but you kind of don't know which state any given atom is in. And now basically what we're kind of starting to control is the spatial structure of those correlations. So it's something like, in the simplest case, if we have the magnetic field gradient, and we have only local interactions, you would expect that instead of those correlations being sort of all to all, the form of entanglement is that each little ensemble is its own entangled state. But now if you turn on interactions at some distance, if I just had two ensembles, to lowest order, it would generate some kind of two-mode entanglement between those, like some two-mode squeeze type of a state. And then more generally, if you have some complicated graph of interactions like the Möbius strip, I'm not exactly sure how to think about those states. That's kind of something we're trying to wrap our head around. I think to some extent, this kind of momentum space picture might be helpful, that one is sort of generating, controlling sort of how much squeezing there is in different momentum modes is perhaps one way to think about it. I do think that these graphs we're drawing are saying those bonds tell you something along the lines that if you cut those bonds that are strong, there is sort of entanglement between the two halves. There's some entanglement between the two halves if you're cutting these bonds.
So also in the new geometry, you cannot describe the whole thing without entanglement.
Sorry, so I think the new geometry is actually a way of sort of seeing which things are, like if I only have to kind of cut one bond, then that would tell me there's like to sort of break that geometry into two halves, that would tell me there's like relatively little entanglement between those two halves. If I need to cut many bonds to break the system into two halves, that would tell me there's kind of more entanglement.
Yeah, thank you.
Yeah. Mm-hmm.
Further questions? No, this doesn't seem to be the case anymore. Thanks again, Monika, for this nice.
Yeah, thank you so much for the invitation.
And thanks also that you have time for a couple of meetings. So they're taking place tomorrow, I think, right? But
yes, yeah.
Great.
Yeah. Great. Okay, see you.